Okay, welcome. Another week. So this is going to be the last week before the third exam, which deals almost exclusively with acids and bases and the mixtures we make and the buffers we make and all that other kind of stuff. So all we're going to talk about this week is going to be what happens when we mix acids and bases. So we're going to start by mixing acids with strong bases and kind of see how the pH changes, all that other kind of stuff, and what that looks like. And this is all under the header of titrations, right? So titration is when we add base to an acid until it is neutralized, right? So we'll start with probably the simplest example, which is what if we have a strong acid? I'm going to use HCl because that's kind of our default strong acid, and a strong base like sodium hydroxide. Okay, so let's say that we start with a solution of 50. We'll put a title on this one: titrations of strong acid with strong base. Right? So what titration means is that we're going to add small amounts of the base to a solution of acid. So let's start with our solution of acid. Let's say that we have a 50 milliliter solution of 0.1 molar HCl. Right? Not a terribly concentrated solution, but still, right? 0.1 molar. Okay, so this is easy to figure out the pH because HCl we know has a very large equilibrium constant, has a very large Ka, and so the pH is going to be the negative log of the concentration of H plus, which we can assume is equal to 0.1. So of course the negative log of 0.1 is 1. The pH of our initial solution is going to be 1. So I'm going to keep track of what our pH is. We're going to have a graph over here. This is going to be our initial solution. And on this side, we're going to have pH, and that's going to go from 0 up to 14. Right? So starting at our initial point, our pH equals 1. Okay, so now what we're going to do is we're going to add some sodium hydroxide. So I'm going to use sodium hydroxide that is the same concentration as our HCl, just because I think this generally makes it a little bit easier. And now there's a couple of points that we want to talk about. First of all, what if we add, well, we're going to do a couple of different examples. If we add 50 milliliters, right? So at 50 milliliters, we are going to have the same amount of sodium hydroxide as we are HCl, right? 50 milliliters times 0.1 molar, we're going to have, what does that come out to be? 5 times 10 to the negative third moles of hydroxide. We're going to have 5 times 10 to the negative third moles of HCl. So we're going to have equal amounts of OH minus and H plus. And of course, we know what that looks like because anytime we have OH minus and H plus in the same flask, we know what their concentrations are going to work out to be. So after we've added 50 milliliters, right, 50 milliliters added, we know that these two numbers will be equal because we know that OH, concentration of OH times concentration of H plus is going to equal 10 to the negative 14th. We know that both of them have to be, oh, stick with me here. I'm losing my pen. I don't know what's going on. 10 to the negative 7th, right? And so that means that the pH, of course, is the negative log of 10 to the negative 7th, which is 7. So at 50 milliliters, we have a neutral pH. So now the question is, and of course, once we add more sodium hydroxide, the pH is just going to keep increasing until, right, we get to a point where we have nothing but hydroxide present. So the question is kind of what happens between this point and this point? Is it a straight line from here going up to our pH 7, right? Or is it a curve of some kind? And so what I think is kind of a nice illustrative example is what if we look at what happens 1 milliliter before? Right? What if we only add 49 milliliters of sodium hydroxide? We would expect, of course, the pH will be lower than pH 7 because, again, right, we have more HCl present than we have sodium hydroxide. But I think if we think about this kind of just in a predictive way, we would expect that the pH would be almost 7 because there can't be very much HCl around at this point, right? Well, the only way we can figure this out is if we use an ice table. So I'm going to do that really quick here. So for HCl, right, H plus is HCl. Right, this is how much HCl do we have? Our initial HCl at this point is 50 milliliters times 0.1 is 5 times 10 to the negative third moles of H plus, right? And I get this number from taking 0.05 liters times 0.1 molar, right? So again, volume times concentration gives us moles. We can do the same thing for OH minus, right? This is our sodium hydroxide. And initially we will have, with 49 milliliters of a 0.1 molar solution, we're going to have 4.9 times 10 to the negative third moles. Right? So both of these numbers come from our volume times our concentration for the corresponding whatever. Right? Now come back to me, we get change. And the change is going to be that, of course, both of these are going to react completely with each other and make water, right? H plus and OH minus, we have strong acid, strong base. The equilibrium constant for this reaction is, of course, very, very large. We know what the equilibrium constant is for this reaction. Oops. OH minus goes to water, right? The equilibrium constant for this reaction is 10 to the 14th. It's a huge number. And so the equilibrium is going to lie very far to the right. There will be almost no H plus or OH minus remaining except for whatever is in excess. And so all the OH is going to react, minus 4.9 times 10 to the negative third. And that means that because the stoichiometric coefficients of the H plus and the OH minus are equal, we get the same change over here. Now we can fill in our equilibrium concentrations. 5 minus 4.9 is 0.1 times 10 to the negative third. That's our concentration of H plus once these two things react, once we've taken 49 milliliters and 50 milliliters here, right? That's how many moles we have. And then, of course, we have 0 moles of OH minus because all of the OH minus gets consumed. Think of it in terms of limiting reagent, right? The OH minus gets completely consumed. It is the lower, we have fewer moles of OH minus around, so this goes all the way away, and only the excess H plus is remaining. So we have 0.1 times 10 to the negative third moles, and we have 99 milliliters. So we have 50 plus 49 milliliters. Okay. And so now we take whatever this is, 0.0001 divided by 0.099. This is moles, this is liters. This gives us a molarity. 0.0001 divided by 0.099 ends up being 10 to the negative third. And so the pH at this point in our titration, where we are 1 milliliter of sodium hydroxide away from reaching neutrality, is 3. Did you expect that? I don't think you did. I mean, I would be surprised if you did, because it doesn't really make cognitive sense, right? We would think that as we get closer to the endpoint, the pH should be going up and approaching 7. And in fact, that's not at all what happens. What happens is right up until we reach that equilibrium point, right, where the concentration of sodium hydroxide is the same as the concentration of HCl, right up until that point, it's an incredibly acidic solution. The pH stays around 3 right until we get to the point where it's 7. And so if we're drawing this, of course, 3 is not 1. Oops, come back. Right? 3 is not 1, and so this is going up slightly as we go, but it's really not getting very far because we would expect 3 to be about, right? So this is, if this is pH 1, this is pH 3, this is pH 7, right? We're getting to pH 3 right about here, and then we got to kind of just go straight up. And this is what happens, right? As we go past this point, right, we start to get we get the opposite, where the concentration of hydroxide ends up being the driver of the pH, right? And we can calculate the pOH and then subtract from 14. But this is what a titration curve looks like for a strong acid and a strong base. Our midpoint, this is our equivalence point, is what we call this, where we have the pH, or we have equal concentrations of acid and base. Concentration of acid equals concentration of base, right, occurs at pH 7. Right? So when we use a strong acid and a strong base, the equivalence point is always at pH 7. And when we have more acid than base, the pH is very low. When we have more base than acid, the pH is very, very high. Okay? So we got one surprising result, right? Acids tend to stay acidic until they absolutely cannot anymore, and we get to that equivalence point. And this is a really fun, I'm assuming that you guys do this in lab at some point or have done it in lab. This is a common high school chemistry lab thing, right? Where you get the indicator in there and it doesn't change, doesn't change, doesn't change. And then all of a sudden, boom, it goes from acidic to basic in like 1 drop or 2 drops, right? And so seeing that, this is the math that kind of backs it up. It's all equilibrium constants. Okay? So next we're going to talk about weak acids, because of course weak acids are a totally different result than strong acids. And so we'll talk about what happens when we take a weak acid and add strong base to that. So that's the next video.